Yes. You learned about all these things already. So basically, if we have a topological space, um, any collection of open sets whose union is the entire space X is called an open cover of the topological space. Okay, let X be a topological space. A collection G of open sets in X that whose union contains X, whose union is X, whose union is X, is called an open cover of X. So what is that? G is a collection of subsets of the topology, is called an open cover of X if union G in G is X. I can talk about the open cover of a subspace also. If Y is a subspace of X, if G is an open cover of Y, if union G contains G, contains Y. Here it is equal to X, there contains Y. And any subcollection of G which also covers X is called a open subcover of G. Okay, any subcollection of G which is an open cover, which is a cover of X, is called a subcover of G. G is a cover, and a subcollection of that also covers X, so that's called a subcover. And in that subcover, and okay, basically compactness is that every open cover of X admits a finite subcover. I say the topological space is compact. A topological space, there's a definition. X is said to be compact if every open cover of X admits a finite subcover. It admits a finite subcover. That's what. Yeah. We'll see. Actually, very easy to characterize what spaces are compact and things like that. Okay. We'll give you examples. In due course of time, we actually prove that in the real line, any set which is closed and bounded is compact. So you have plenty of examples of compact sets. In the usual topology R, any subset of R which is closed and bounded is compact. We'll prove that. Then we'll have plenty of examples of compact sets. Okay. We'll also prove that if I have, several topological spaces, each of which is compact, then the product of all topological spaces is also compact. This is a very tricky theorem. We'll prove that the product of all spaces is compact, which is actually a little difficult thing to prove. It's called Tikhonov theorem. This is an interesting thing. It's not because you're taking not a finite collection, you're taking an infinite, arbitrarily large collection. X alpha, alpha, and delta is a family of compact sets, then there is an X alpha, alpha, and delta coming with the product topological space is compact. Box topology doesn't do the job. So we will have examples of compact logical spaces. once we resolve some theorems. Yeah.
So a subcover is also a cover of X essentially.
Yes. 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 Yes.
Uh, yeah, that's why it's okay. It's G is not the minimal set. I mean, you can actually make it smaller and smaller
Yeah.
if small makes sense, because you can take a cover of X and then find a subset of that. If it is compact, you can find a subset of that, which is a cover of X, and then subset of that and subset of that, isn't it? Or am
Yeah.
I missing something?
Yeah. Yeah. It's
Yeah.
true. Yeah. Yes, that's true. What we are
So
saying
for
is
a
that.
compact,
Mm,
so for a
mm.
compact set, if you have a cover, you can always find a smaller cover, essentially.
No, essentially, you can find a finite subcover. If you have already a
Finite
finite
sub.
subcover, which maybe it's a minimal subcover, we don't talk about those concepts, but they can probably
Yeah, yeah.
talk. Once you have
Okay,
minimal
okay.
subcover, you have no more a subcover anymore, right? Essentially,
Right.
you don't need a whole lot of set to cover X.
Yeah,
That's the point. X, a
right.
compact set
That's
can be covered with finitely many open sets. That's what the compact set is. Okay.
okay,
For
okay.
example, if X is an infinite set, if X is an infinite set and you have the discrete topology on it, okay, I think every subset of X is an open set. So if you want some subset to be, I didn't talk about subset being compact. If subset is compact means subset inherits some topology from the topology of X, right? So it has its own topology. Subset has its own topology. With respect to that topology, it's a compact space. Then that subset is said to be compact. So in that sense, if I'm going to look at subsets of X and they want to be compact, I think the only way any subset of X will be compact is it's a finite set, because every singleton is an open set. So I don't, it's right. For covering that finite set, you have to have minimum that many singleton open sets. Okay. If you have an
Right.
infinite set of subset of X, that cannot be compact, because all the singleton sets will cover that infinite set, but that cannot have a finite subcover. Is that clear? So compactness is a very rigid condition. In this case, compact means the set is finite. Okay. So here is still a definition. A subset Y of X is said to be compact if Y is a compact topological space by the topology it inherits from X. Y is a compact topological space with the topology it inherits from X. Okay. So this example we talked about is very, very nice. X with discrete topology. So what is the topology here? For set of X, right? What are the compact sets? Only finite sets. If I take an infinite set, uh, all the singleton elements, all the elements you have the infinite subset maybe Y of X. All the singletons will cover Y. It can have finite sub, it cannot have finite subcover. You cannot reduce any one of them. Okay. So infinite sets are not compact. So compactness is very rigid condition. Okay. Of course, in a general topological space, I can have big chunks. Okay. Even then, it may be infinite subsets or whatever it is. Even then, it can be compact depending on what the space, as we'll see. T is powers of x. Then any subset of x is compact if not if it is finite. if and only if it is finite. Only finite subsets are compact sets. Of course, if you have indiscrete topology, then you have only empty set in the whole space are the only topological open sets you have. Then, of course, every subset is compact. Okay? Because you don't even have infinitely many open sets. That is the other extreme. Is that okay?
Yes, yes.
Here is the first theorem I prove. Any closed subspace of a compact topological space is compact. Any closed subset or subspace, you can say. Okay. So any closed subspace of a compact space of a compact space is compact. If I have a compact topological space and Y is a closed subspace, so Y has to be compact too. Proof. Let X be a compact topological space. Okay. And Y be a subspace of X. Not every subspace will be compact. Only closed subspaces will be compact. Okay. Not at the opposite direction. Compact subsets need not be closed, but if some extra property is there in the topology, they will be closed. Okay. For the present, I'm not talking. So, if I take a closed subspace of compact space X, that Y has to be closed. Y has to be compact. So, if you want to show Y is compact, you have to show that Y with the topology on its own right. It is a topology already inherited from X. With respect to the topology, Y is compact. That means every open cover of Y in that topology of Y admits a finite state cover. Okay. Let G consisting of all G alpha, alpha belongs to delta, be an open cover of Y. Actually, what is G alpha? G alpha is an open set in Y. That means G alpha is actually Y intersection H alpha for some H alpha in the open set in capital X, right? For each alpha in delta, there exists a open set H alpha in X. There exists open set H alpha in X such that G alpha, okay, G alpha is H alpha intersection Y. That is how the open sets in the subspaces are going to look like. Open sets in subspace are intersections of open sets of X with the subspace one. Okay. So also we given that it's a cover of Y. So union G alpha is equal to Y. Okay. Union G alpha, alpha in delta is Y. Okay. So notice capital H, which is all H alpha, alpha in delta. Oh, they are actually bigger than G alpha. They all cover already Y. All the H alpha will, their union will contain Y. Okay. But the Y complement alone is a closed set in Y complement alone. If you look at it, there's a close, that's an open set. Y is closed in X. So Y complement is an open set in X. Notice Y complement is open in X. So somehow or other, all the HFRs will cover Y. If necessary, Y complement will be there for covering the Y complement. So the whole of X. So this is a cover of is an open cover of X. And X being compact, this open cover admits a finite subcover. That finite subcover will be some H alpha 1, H alpha 2, H alpha n, maybe Y complement also. It may be there, but even without that, I may be able to cover. Okay. Since X is compact, there exists, finitely many. Okay, there exists H alpha 1, H alpha 2, etc. H alpha n, finitely many, finite subcover. There exists a finite subcover, right? Such that, okay, union H alpha k equal to 1 to n, and maybe I need Y complement, I don't know, union Y complement is X. If these things, if themselves cover X, I'm happy. If they don't cover, maybe Y complement is also there. In the entire cover, Y complement is there. So in the subcover, Y complement can be there too. Many times you need Y complement, but that covers X. The Y is not covered by Y complement. Therefore, Y is part of X and is not covered by Y complement. So Y has to be covered by this. Therefore, Y is a subset of union H alpha K equal to 1 to N. Oh, therefore, Y is equal, therefore, Y equal to Y intersection union H alpha K equal to union H alpha K equal to 1 to N, and that is union K equal to 1 to N, Y intersection H alpha K. Now that is your union G alpha K equal to 1 to N. There you go. I have found a subcover of G, right? I have found a collection finitely many elements in G whose union contains Y. Thus, G alpha K K equal to 1 to N is a finite subcover of Y. So this proves that Y is common. This proves that Y is common. Okay. So every closed subspace of a compact topological space is compact. Clear, right?
Yeah, I'm just thinking that one of the edge cases, what is it possible that only Y complement, just Y complement can be an open cover of X? Basically, there are no such alphas needed. It cannot be, right?
No,
Because
there is X and this is Y.
Y, yeah.
Y complement will skip the Y completely. So I have to have some H alphas which should cover
Yeah,
that.
some H alpha has to be there to cover
And
that.
all those H alphas are good enough for me to cover Y.
Yeah,
Because Y
Y
complement
itself.
means yeah.
Mm.
So this is nice actually, you know. This will allow me to create lots of examples. Okay. Next, another thing. Continuous image of a compact set will be compact. If you have a topological space X and a topological space Y, and here I have a continuous function. If X is compact, the range of F, that is F of X, will be a compact subspace of subspace Y. Okay, the continuous image of a compact set is compact. So, a continuous image of a compact set is compact. I will write even that is if x comma y are topological spaces and f from x to y is a continuous function, is continuous. Okay. If x is compact, then f of x is compact too. Okay. And x is compact. Then f of x is a subspace of y, is a compact subspace of x.
Compact subspace of Y.
Subspace of y, thank you. That will be very easy. Same way, you have to take an open cover of f of x, and if you pull that open cover back to the domain space, it will cover the whole of x. And so it should have a finite subcover, and that you push forward. That becomes a cover for f of x. That's the proof. Okay. Let G, consisting of some G alpha in delta, be an open cover of f of x. Actually, there is a subspace of y. So these G alphas are actually fx intersections from H alphas, where H alphas are open in y. For each alpha in delta, there exists a open set H alpha in y such that G alpha is f of x intersection H alpha. All these H alphas are going to be on the right hand side. I think all the H alphas will cover fx the range. Okay, G alphas themselves are covering fx, so H alphas will cover fx. So fx is equal to union G alpha in delta, and this is contained in union H alpha in delta. And therefore, if you pull back, you see x is contained in f inverse union H alpha in delta, but the inverse has that property. You can write it as union alpha in delta, f inverse H alpha. So this is going to be a cover of x. So H equal to set of all f inverse H. Okay, H is f inverse H alpha in delta is an open cover. Basically, remember which alpha is open, f inverse H alpha is open because f is continuous. Since f is continuous, okay, is an open cover of x. That's because, since f is continuous, each f inverse H alpha is open in x. That's right. So this is an open cover of the compact space x. Since x is compact, it is going to admit H admits a finite subcover. What do you mean by that? There exists alpha 1, alpha 2, etc., alpha n, finitely many of them in delta, so that x is equal to union F inverse H alpha K equal to 1 to N, okay, which is F inverse union H alpha K equal to 1 to N. That's it. So if you take F on both sides, you get the content. Hence, F of X is contained in union H alpha K equal to 1 to N. In particular, a corresponding G alphas will make sure. Therefore, Fx is equal to union G alpha K equal to 1. So this proves that Fx is compact. Okay. Continuous imagine of compact sets. Is that all right, sir?
Yep. Yeah.
The very definition also gives me one interesting fact. What are you saying? That every open cover of the compact space admits a finite subcover. If you look at the complements of the sets of the open cover, they become a collection of closed sets whose intersection is empty. So I find a finite subcover for the open cover, and therefore I get finitely many of those complements which are closed sets. Their intersection should be empty. So if I have a family of closed sets in a compact topological space, and the intersection of all of them is empty, then only finitely many of them amongst them can be obtained. Their intersection will be empty. So here is the theorem comes right away from the very definition, which says that a space X is compact if and only if for every collection of for every collection of if and only if every collection of closed sets in X with empty intersection there exists a finite subcollection finite subcollection with empty intersection. I can have a whole lot of closed sets whose intersection is empty. Then that intersection is empty not because there are so many, just you can have finitely many amongst them. They themselves intersect to an empty set. That is, X is compact if and only if for every uh, uh, given any collection of closed sets C of closed sets in X with intersection C and C empty, there exists finitely subcollection C1, C2, etc. Cn of C, whose intersection is empty, with intersection Ck equal to 1 to n is empty. Is that clear?
Yeah.
Just instead of open cover, what we are doing is taking their complements. So it's a closed cover. Okay, as not closed cover. A collection of closed sets whose intersection is empty. It will happen only when there is a finite subcollection of amongst those closed sets whose intersection itself is empty. Okay, follows very much from the definition. Okay, it's just equivalent to the definition of compactness. Okay, the result is a reformulation of definition of compactness. So you don't have to really worry about it. Okay, here I'll introduce a notion of what do you mean a collection has a finite property. I say collection of any sets has finite section property if it has a finite subcollection which is non-empty intersection. Okay, maybe every finite subcollection has a non-empty intersection. Yeah, that's right. A collection C of subsets of a set X is said to have finite intersection property if every finite subcollection has non-empty intersection. If every finite subcollection of C has a non-empty intersection. Every finite subcollection has a non-empty intersection. Okay. Whatever I stated there, it becomes a very easy theorem for that. What is it saying? If the entire intersection is empty, then a finite subcollection should have empty intersection. If every finite subcollection has non-empty intersection, the entire intersection should have be non-empty too. Clear? So what is the theorem? A topological space X is compact if and only if every collection of closed sets having finite intersection property, every collection of closed sets that has finite intersection property has to be non-empty intersection. Every collection of closed sets with finite intersection property as a non-empty intersection. Is that clear? Every finite subcollection has an empty intersection. The whole collection of closed sets cannot have empty intersection. But if it has empty intersection, according to the above obvious equivalent formulation, if the entire intersection of closed sets is an empty intersection, finitely many collection amongst them will have itself an empty intersection, but no finite subcollection has empty intersection. That's what finite intersection property is. So if it has a finite intersection property, no finite subcollection can be non-empty, and therefore the entire collection of closed sets cannot have non-empty. Proof is done. This is just a corollary. This just says whatever the theorem said. This is equivalent to the theorem. This is equivalent to the above theorem.
Just restating.
Restatement. So oftentimes proving compactness is done like this. Actually, we do even better. You're trying to say that every open cover admits a finite subcover, right? That is how came out to have a closed collection of sets whose intersection is empty, has to have a finite subcollection which is empty. Okay, so if a closed collection has a finite intersection, collection of closed sets of X has a finite intersection property, then every finite subcollection has non-empty intersection. Therefore, the whole space has to have whole collection of closed sets must have non-empty intersection too. Now, this I can go back, I don't have to prove the space is compact means every open cover admits a finite subcover. I can do something better. We can only prove that the basic open sets of X has a finite subcover. You know what? You can even prove that some basic open cover of X has a finite subcover. If you have collection of, if you have a subbase and the open sets of them cover X, then it should have a finite subcover. And that is equivalent to prove that the space is compact. But that result is a little difficult, and in proving that only we need to get into some things. So here is the theorem. First of all, this is the easy theorem to prove. A topological space is compact if and only if every basic open cover admits a finite subcover. Okay. Well, compact implies every basic open cover admits a finite subcover, because every open cover admits a finite subcover. It's only the other way around you have to prove. That if every basic open cover admits a finite subcover, then every open cover also admits a finite subcover. So here's the proof. Suppose B is a base and G is a base. Suppose B is a base for a topological space X, and G is a G means G contains a lot of G alpha in delta. Be a basic open cover of X. In order to show it's compact, I will show it has a finite subcover. I will assume this condition. Okay, assume the condition and prove. You're proving only one side. Otherwise, maybe a topological space is compact if other side is obvious. If every open cover that admits a finite subcover, every basic open cover admits a finite subcover. Okay? I only want to prove this part. Other part is obvious.
Yeah.
So that's why I took any G alpha and delta be a basic open cover of X. I have to prove. What are the open sets? Open sets are arbitrary unions of members of basic open sets. So basic open sets, how does it generate topology? Every open set of the topology is union of some members of basic things. So each G alpha is a union of basic open sets from B. Okay, so if I look at every G alpha has some basic open sets. So for all alpha, you have all the basic sets you have created, and all of them will create a GB, and maybe I should use some other name, B dashed, which is each B of the basic cover, where B is contained in is part of the description of G alpha. Okay, B is part of the description of G alpha. Thus, that B is contained in G alpha for some alpha in delta. Actually, I could say B is part of the description of G alpha. I could say that, but B contained in G alpha. This is also good. Then you see that B dash is a basic open cover of X. Because all these such B's is making up G alpha, and although G alpha is covering X, therefore all these B's also cover X. And that basic open cover, it defines subcode. So this B dash by hypothesis admits a finite subcode. Okay. Oh, so each element I have in this finite many, each is in say finite subcode, say B1, B2, etc., Bn. But each B1 is in some G alpha. So for each K, okay, there exists a alpha K in delta such that Bk is contained in G alpha K. So I think we're done. Therefore, X is equal to union G alpha K equal to 1 to n. Actually, union B of Bk itself is X, and they are contained in this, but that is actually equal to, there's no more contained, where there's contained X. So this completes the proof. Okay. The next result is about subbasic open cover. Okay, topological space X is compact if and only if the subbasic open cover is. The subbase is what? If you have finite intersections of the subbasic elements, will become a basis or open base for the topological space. Then you call them sub. We'll prove that. I'm not going to prove it today. That a topological space is compact if and only if every subbasic open cover admits a finite subgroup. There are also one-side articles. Okay. And actually, I can also prove equivalently that any collection of subbasic closed sets. What do you mean by subbasic closed sets? That means their complements make up a subbase. For the topological space, I can talk about subbasic subbasic closed sets. Okay. So any collection of subbasic closed sets having finite intersection property, the intersection of all the subbasic closed sets must be non-empty. And that is equivalent to saying that X is compact. I don't know if I want to prove that or not. It's a long story. Okay. I will explain that. I will explain the proof. Now, in order to go forward, I need a few details in the theory, especially Johnson. So maybe we'll stop it here and talk about a little bit of a set theory. At least after I state John's lemma, I'll come back and prove this. Okay. I'm not going to do a whole lot of set theory. I'll just go straight ahead. A lot of things are actually, there are three things: action of choice, well ordering principle, and John's lemma. All these three are equivalent. Okay, all these three are equivalent. Though action of choice looks very easy to see, then you suddenly wonder, well ordering principle becomes very like, is that really true? And John's lemma is another interesting thing. So I think when people saw well ordering principle, then they were worried about action of choice. Okay, we talk about all these things. Maybe I'll first explain John's lemma. Then I talk about what is ordering and so on, and what is this well principle, what is that. I'm not going to prove anything. I'll just state all those things. I don't prove the equivalences of them. And
Yeah.
Naive Set Theory by P.R. Halmos is a wonderful book, which explains all these things very deeply. We should also start with Piano's actions. There is no end to it. We have to talk about what countable sets are, uncountable sets are. I already mentioned the short Wednesday already. What is countability? There is a lot of things. All these things I'm assuming anyway. But I just want to see that I state these things at least once. So, little bit of set theory before I can prove that. Okay. First, order. Order is not a very big thing. The usual order that we talk about in equal is whatever properties it has, we want to retain that. First of all, if you're given a set A, any subset of A cross A is called a relation on A. Okay? Let A be a non-empty set. Okay? Any subset R of A cross A, any subset R of A cross A is called a relation on A. Okay? If AB R is a subset of A class A, R is a subset of A class. R is ordered pairs. So if an ordered pair AB belongs to R, we say A is R related to B. Okay, it's like less than or equal to. You say A is less than or equal to B when B minus A is positive. When in real numbers in the real line. What is A less than or equal to B means? So you know what A less than or equal to B means, but that's connecting A and B. So, for example, 2 is less than or equal to 4. So, 2, 4 is an acceptable element. That's in that less than or equal to relation. Okay, maybe 5, 1. 5 is not less than or equal to 1. So, 5, 1 is not in less than or equal to relation. So, less than or equal to is actually collection of all subsets, collection of all ordered pairs A, B, where A is a real number, and so is B a real number, and maybe for B minus A is non-negative. We can visualize that. So a real relation is a subset of A class A. Okay, I can talk, right? And a relation R is called a relation on A. Okay, is called a relation on A. Okay, a relation R on A is said to be, I will do things, is A said to be reflexive if every element in A is related to itself. It's said to be reflexive if A are A for every A in A. Okay, symmetric said to be symmetric only when whenever AB is there, then you ask BA. If AB is not there, don't bother looking for BA. Okay, if whenever if for A comma B in A, for A comma B in A or B implies B or A. If A is related to B, then I want B to be related to A also. If A is not related to B, I have no complaint about B not relating to A. It's said to be transitive if for A, B, C, and A, okay, A or B and B or C implies A or C. That's transitive. Okay. I will mostly write less than or equal to in place of A. Sorry, in place of R. And that's why we are writing the notation like this. AR means A less than equal to A. I use the symbol less than equal to for any relation, keeping in mind what less than or equal to does. Whatever less than equal to do in real line does, if R does satisfy those operations, I want to call that less than or equal to. Okay, just a notation. Okay. A relation on less than or equal to on a, by the way, if all three are satisfied, you call that an equivalence relation. Okay, if R is reflexive, symmetric, and transitive as well, we say R is an equivalence relation. R is an equivalence relation. I'm not going to talk too many things about these things, but anyway, I'm here. So, is an equivalence relation. One would actually see the equivalence relation sort of gives you equivalence classes and things like that. Okay, I don't think I need to talk about them yet. Maybe just briefly I'll say that. Okay, so if R is an equivalence relation, on a set A, okay, for every A in A, I introduce the equivalence relation RA. This equivalence class, okay, consists of all the elements B of A which are related to this A or B. All those things which are related to A is called the equivalence class consisting of A. Equivalence class containing A. So what we are saying is that if the space is like this, okay, if A is there, all its relatives, they all make up a subset of capital A, all the relatives. Maybe B is here and A is not related to B, then no relative of A can be related to B either. So the B will has its own equivalence class, okay, and C will have its own like this. So this once you are talking about equivalence classes, the whole space will be separated into equivalence classes. All the relatives of A and some other element which is not in there, their relatives, some other element which is not in both of them, their relatives, and so on. So it turns out easy to see that the A can be then therefore any two equivalence classes, either they're identical or they're disjoint. Because if they two share, if two of the equivalence classes share an element in common, then every element here is equivalent to element here. Suppose they share element B in common. If I take an A here, take a C in here, then A is related to B and B is related to C, and by transferring A is related to C. Therefore, A, B, C, all of them is the same equivalence class. Therefore, RA and RC are both identical. So any two equivalence classes are either identical or disjoint. Classes are either identical or disjoint. Or disjoint. As a matter of fact, the entire space can be written also as a pairwise disjoint union of equivalence classes. And the entire space A can be written as a union of all of its equivalence classes. Okay? And the space capital A is union of equivalence classes. I don't think I would rather stop. I don't want to go more because the order I am interested in is not equivalence relation. The less than or equal to inequality, okay, is not an equivalence relation. 2 is less than or equal to 3, but 3 is not less than or equal to 2. As a matter of fact, it is not symmetric, it's anti-symmetric. I'm not interested in a relation here. What I'm interested in is this following, okay? So going back, I have not said anything about order here. I just talked about relation, okay? A particular kind of a relation, which is anti-symmetric, is what is called order, okay? Okay, so here is the order. Let X be a non-empty set. Okay, a relation which is symmetric, which is reflexive, anti-symmetric, and transitive is called an order. A relation on X which is reflexive, anti-symmetric. I'll tell you what anti-symmetry is. Anti-symmetric, anti-symmetric, and transitive is called an order on X. Okay, so that is less than equal to is an order on X if what one is reflexive, I said. If A, X less than equal to X for all X in X. 2, anti-symmetric, which is if I take X and Y in X, if X is less than equal to Y and Y is less than equal to X, then X equal to Y. Okay, okay, X less than equal to Y and Y less than equal to X implies X equal to Y. Transitive, X less than equal to Y, Y less than equal to Z implies X less than equal to Z. If these three properties are satisfied, I call that an order. And X together with this order is called a poset. Is called, actually it's called, is called an order or a partial order. Is called a partial order. Partial order on X. And X less than equal to is called a partially ordered set. A set is called partially ordered if there is a partial ordering on it. Okay, a set X is called partially ordered if it has a partially ordering on it. Partial ordering on it. Actually, I should be a little more careful because you can have many partial orders on the same set. So that particular partial order is also very relevant in our discussion. So I might as well say, we might as well say that x less than or equal to is a partially ordered set. Oftentimes we say it is a poset or just a poset. Okay. So if suppose I took a poset, let x less than or equal to be a partially ordered set, be a poset. So then you have some words that I can have. If I have x and y, suppose x is less than or equal to y, I say x is a predecessor of y and y is a successor of x. Okay. For x comma y in x, okay. If x is less than or equal to y, we call x a predecessor. Predecessor. What is the spelling? Predecessor. Oh man, I have trouble. I should write it properly. It's called a predecessor. What can be a good spelling? And trouble.
CSSOR, I guess.
This is why I suppose. Huh? Predecessor. Predecessor. I think one more S will be there. Predecessor. No, predecessor. Huh?
CESSOR.
Predecessor.
CESS.
Predecessor. Okay, sorry.
Predecessor. Okay.
Yes, predecessor of Y. And Y is a success. Y is a successor of X. Okay. You can also have what is called an initial segment for any. Okay. For any A in X, if I look at all X in X, which are, oh yeah, less than should be defined. This less than is not a big deal. I say X is less than Y when X is less than equal to Y and X is not equal to Y. Okay. We also define, also say for X and Y in X, X is less than Y if X is less than equal to Y and X not equal to Y. Okay. So there's a strict predecessor, X is a strict predecessor of Y, something like that. Okay. Right. And for any A in X, we define initial segment. Initial segment of A. Initial segment determined by A. Is S of A, which is consists of all those X in X, which are all smaller than A. Well, sometimes we want to include A also. Then I say weak initial segment determined by A. Okay, weak initial segment determined by A is, I use the symbol S bar A. Nothing to do with the closure and so on. There's no topology here. Consists of all X in X, which are less than or equal to A. There's a weak initial segment. All these are very routine definitions. No, I can talk about a, for example, least element. No guarantee there will be a least element. I can say something is a least element if it is smaller than or equal to every element X and X. Least element is also sometimes called the smallest element or maybe first element. These are also names. Similarly, I can find the greatest element uh, or the last element, okay, to be the element so that everything else is less than equal to that. Okay, I have the least and greatest elements. No guarantee you have least and greatest elements in a general pass set. Okay, if there exists an A, if there is an A in X such that A is less than equal to X for all X in X, we call A the least or the smallest or the first. All are these are names used are the first element of X. Okay, similarly, we can talk about the greatest elements. If there is an A in X such that you see the greatest element, right? If X is less than equal to A for all X in X, okay, we call A the greatest the largest or the last, we can say whatever word suits you. Greatest or largest or the last element of X. Okay. There's no guarantee you need to have greatest elements or the largest element. For example, if you look at a set of all natural numbers with the ordinary inequality, it has least element 1, but there's no greatest element. At the same ordering, if I write it in reverse way, x is less than equal to y, if minus y is less than equal to minus. Suppose you did some reverse ordering there, then you won't have the greatest element, but you have the, when you do that, okay, anyway, I think you understand that. Example, n, in almost, he will also have 0 in the set of natural numbers. He uses the symbol omega, okay? Anyway, n equal to 1 to ad infinitum, a set of natural set of natural numbers with usual inequality that everybody knows, usual inequality as the least element, but no greatest element. The least element, but no greatest element. Right? Yeah. I'll give you one more example. Okay. I can look at, for example, the portion of containment as an inequality. Less than or equal is containment. Right? This also, you can see, is a poset. Okay? Is a poset. I think it's very, can you hear me well now? Can you hear me?
Yeah, I can hear you.
And easy to see that empty set is the least element and the whole space is the greatest element. we can actually, it's a definition. A partially ordered set in which the ordering has the property that any two elements are comparable, then I call such a partially ordered set a totally ordered set, or simply ordered set, or even chain. Lots of names for that. Okay, a poset in which any two elements are comparable. Any two elements are comparable is called, or you can say an ordering which allows you to compare any two elements in the space is called a total order. I can say that also. In ordering, but that's it. Anyway, in ordering, and a set X, which allows to compare any two which allows to compare every pair of elements in X, which compares every pair of elements in X, pair of elements in X is called a total order, and a set with a total order, a set with a is called a totally ordered set, or a chain. We call that also chain. Chain is something we use repeatedly. For example, in a partial effects with containment, I don't think any pair of elements can be compared. What is the comparison here? A is less than equal to B means A is contained in B. What is this inequality for A comma B in partial effects? Okay. We say A is less than equal to B if A is contained in B. So I would directly use the containment in place of less than. Okay, so this is the inequality. You can very well see that if I take two subsets of X, they don't have to be compared. And so this is not a totally ordered set. Okay, so Px, this is not a total order. Okay, I cannot compare any two elements, but I can find a kind of a lower element for a bunch of elements. Okay, right? So we will introduce the notion of ordinary inequality in natural numbers is a total order. Okay, yeah. Right. We'll also introduce, yeah. For example, if I take x naught and y naught are in X, okay, what is singleton x naught, what is singleton y naught? They're not comparable, are not comparable, given that x naught is not equal to y naught, are not comparable. Okay, you can have, of course, chains in power set of X. You can have a whole sequence of subsets which are every two of them are comparable. You can create a chain, a totally ordered subset of power set of X may be created, but power set of X as such is not a totally ordered set. There is a notion of a minimal element and a maximal element. A minimal element means something which has no other elements below that. So I'm going to say that A is a minimal element of X. If anybody says that X is in X and X is less than or equal to A, that means X has to be A only. There is nothing else which is a strict predecessor of A. Then I say A is a minimal element. Similarly, I say something is a maximal element. I say A is a maximal element in substance. That's the biggest one, right? Not biggest one. That's the maximal element. That means that means if any x is there, so that A is less than or equal to x and x is in x, it means x has to be A. There's nothing bigger than A. Maximal element does not mean it's bigger than every other element. Many times it may be not be comparable to other things. Maximal element does not mean it is bigger than every element. It means that there is nothing bigger than that. Let's refine these things.
Isn't that same as least and greatest?
No, 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 no. For example, singleton x naught in power set of x. Okay. Uh, yeah, even this is also not going to do. No. Um, I can have an inequality like this. This is the smallest one. Next, 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 next. This one, for example. Maybe I can write in this way. Okay. So you see that this is a minimal element. There is nothing below this, but there are things which are not comparable to that. This is not a minimal element, it has smaller elements than that are there. This is a maximal element, but that is not bigger than equal to everything else. Okay. So inequality is like this: A, B, C, D, E, F. So you've given that A is less than equal to C, C is less than equal to D, D is less than equal to F. Of course, you can see transitivity, everything. Reflexivity, A is equal to A. Reflexivity, antisymmetric, and transitivity will follow when you write like this. Now, A is a minimal element. It is not the least element. Okay? E is the maximal element. It's not the greatest element. If I had a situation like this, I can say H is the maximum or the greatest element, but there is no least element. Okay. So let's give the definitions. Let x less than or equal to b. I think I'm taking. I should maybe see what is the time now. Yeah, I should stop soon. After this, I will stop. I'll continue the discussion tomorrow. Let x less than equal to b. X less than equal to b. A partially added set. Okay. An element A in X is said to be a minimal element if for every X in X, X less than equal to A implies X is equal to A. That means there is nothing smaller than A in that. An element A in X is said to be a maximal element, maximal element of X. If for any X in X, A is less than equal to X, nothing should be more than X, A, right? Less than equal to X implies A equal to X. So here is a clear example. So this example is good. So I'm not going to explain the whole inequality. Going up is inequality, strict inequality. Okay. So going up is the inequality. So if that is the case, so a quantity is less than equal to that if the level at which it is below the level of the other one. In that sense, you see that A, B are minimal elements. BE are maximal elements. Okay. If you look at as an example, uh, let S be the set of all. First of all, let X be an unempty set, be a non-empty set. Maybe having more than one element will be better. Let S be the power set of X minus empty set. So collection of non-empty subsets. Empty set is removed from there. Okay. So you see that every singleton set is a minimal element, right? Then and contain less than inequality is what? Inequality is containment. Is containment. So yes, together with containment. Okay. You can see that then every singleton set, a singleton X naught, where X naught, where X naught is in X, is a minimal element. Is that clear? There is no least element at all in this. Because I removed the empty set. This has no least element. There is no least element. There is a greatest element though. The whole space X is the greatest element. Okay. Whole space X is, however, the greatest element. Actually, you won't have any more the greatest element. So if I just take a general poset, I may not have the greatest element or the least element, but I would like to have them. So here is a wonderful result, which says that if every chain in the poset has an upper bound, the entire poset should have a maximal element. Okay, greatest element probably don't. It has a maximal element. That's what Jones lemma says. If every chain has a upper bound, then there is a maximal element in the poset. You cannot avoid. Of course, there need not be a maximal element. You have noticed that if you look at set of all natural numbers, it has no maximal element. No greatest element, no maximal element also. Okay? But it has minimal element. Indeed, it has the least element. So what John's lemma says is that, I'll state it tomorrow and maybe I have to say more things on that. Says is that if in a poset, if every chain means a totally ordered subset. Totally ordered subset means in that subset, any two elements are comparable. If every chain has an upper bound, then the entire space should have a maximal element. That is what John's lemma is. I will state that in the next class because there are a lot more things we have to talk about after that is stated. Maybe I'll just state it. Okay, John's lemma. Okay, let X less than or equal to be a partially ordered set. I didn't talk about upper bound. It's very easy for you to understand what I mean by upper bound, right? Okay, if I had not defined that separately, if every chain in X has an upper bound, every chain in X has an upper bound, then X has a maximal element. This is what George lemma is. Usually, if you want to get the maximal thing, this is what we do. We look at the collection of all such things and introduce an ordering on it and prove that every chain has an upper bound. Then it shows you there should be a maximal element. Okay? I'll stop my discussion here, it's already 4 o'clock, and we continue this discussion. How is it so far?
Yeah, that's fine. We don't need to write everything just so, I mean, a lot of these concepts are similar. So, I mean, familiar with, so we can, yeah.
Right on.
Yeah.
Only just a little, instead of saying we are talking about maximal elements and minimal elements, this is
Yeah.
probably a theorem. I don't know. You may have used this theorem. I don't know. You may have used this.
No,
Huh?
no, I haven't actually. I didn't read about it.
Also, a set is said to be well ordered. In some sense, if every a non-empty set, the subset of it has a least upper bound. Okay, for example, instead of all natural numbers, it's such that whatever subset you take, you have a least element in that. But in general, you want to look at the negative integers. There are lots of subsets which do not have least elements. Okay, so what will be surprising is like John's lemma action of choice to show that no matter what set you bring, I can always create an ordering in that, which ensures that it has every non-empty set has a least element. That's a little crazy. Okay. Anyway, we'll talk about all those things in the next class. We'll stop here. All right.
Okay.
All right. Okay, so take care.
Yep. Thank you. Yeah. Well.